Okay, in this video I'd like to talk to you about the concept of work. There's one thing I'd like to point out, and that is that most textbooks, including our own, refer to work, which is a noun. I'd like to try to at least occasionally use the term a force working to emphasize that what's happening here is not that you have something tangible. I mean, energy itself is not tangible in the first place, but then the question of what work is sometimes very unclear. What work is, I think, can be made more clear by emphasizing it's a verb, it's a process, it's something that a force is doing. Let's start out with the idea of conservation of energy and asking how can the idea of conservation of energy account for the fact that you can just pick up a ball from the ground and you can throw it. So we have this image from a previous video, and the ball initially has no kinetic energy and it has no gravitational potential energy. It's just sitting there on the ground. But after you throw it, it has both. So what gives? And I suspect you all know that the answer to this, it comes in terms of the person has muscles that have energy stored in the form from various foods that we consume, and you can turn that into an internal energy, and you can turn that into throwing the ball. And that's exactly the point. The energy doesn't just come from nowhere. It comes from somewhere. And right here in this class, we don't have to trace it mathematically from the chemicals and the muscles. We're able to say that the system is the ball and the gravitational field of the Earth, and it's the Earth's influence on the space around it. So the person can exert a force on the ball and accelerate it, and then once the person and the ball are not in contact anymore, the person is not a part of the system, meaning they can't influence the motion of the ball once the question starts. We define the question as the moment after the ball has left this person's hand, so there's no hand force, and there's an initial velocity at that point of 13 meters per second, and the hand is done accelerating the ball. Only G is able to cause acceleration at that point, the gravitational field of the Earth. So the energy of the system, which is the ball plus the gravitational field, that's conserved throughout this projectile flight. Prior to that, it does experience an outside force, which is the hand. And then after the question is over, the ball hits the ground, and it experiences that as an outside force also. If we wanted to make the problem bigger in scope, to include more in our system, we could do that. We could say, for example, that from the perspective of the entire planet, the total energy in the system did not change at all during this experiment. That's usually not the most useful thing for us to do for one of these problems that we're given. So I just wanted to sort of start that out with the idea that we know that energy can enter a system and it can leave a system, and that doesn't mean it's created or destroyed. It means that something is adding energy or taking energy from the system. The ways that an object or system can interact with their surrounding environment, including transferring energy, is covered in the study of the first law of thermodynamics, which is chapter 15 in OpenStax, and it's not really part of our Physics 140 course, nor Physics 150. The energy can be changed by having an external force working on the system. So external forces, for that reason, are called non-conservative forces for your system. And again, as I mentioned in the previous video, heating and radiating are other ways that energy can be transferred into or out of a system. They're just topics that we're not covering in this course. They would be part of a thermodynamics course, or they may have come up in chemistry. I want to emphasize that work, and therefore change in energy, can be negative, but it's not a vector. And so much like when we were talking about energy, having it not be a vector is very helpful. When work is calculated to be greater than 0 joules, then that means that you have added energy to the system. And if work done by some non-conservative force is less than 0 joules, then that means that that force has removed energy from the system. One of the ways that you can determine the amount that a force is working is as the integral of a graph of force versus displacement. And the graph here in the middle, the force versus displacement is the shape of a rectangle. That's what you get with a constant force that's acting. Notice the other one, though. There's a changing force. This is actually a graph that we've seen before. We want to make sure that we talk about that at least a little bit. You hopefully recall this experiment from a previous video, and we had a non-constant force in that video. It looked a lot like on the previous slide and then on the next one. So when a spring is being stretched, the force measured is not constant, and then you would want to be able to account for that when you're calculating the work done by that force. So our equation, as it's given on the equation sheet, is that the work is equal to the average force times the displacement of the object that the force is acting on, times cosine theta. And I'm going to explain what the delta x means and what the theta both of those mean here in the following slides. I want to point out that the average force aspect of it really only applies for us because of springs. In the real world, if you have a question where like some kid is pushing on a block, that kid might not push with a steady force throughout the entire experiment. But for our questions, a force will be constant in every scenario I can think of, except when you're talking about something that is elastic and obeying Hooke's law. So if something is given as this person pushes with 18 newtons of force, that is the average force that person is pushing with. And the fact that it's listed as average in our equation is entirely because it would matter to Hooke's law. When I did that experiment that was on the previous slide, in the earlier video I showed you what the spring constant was. I took the slope and I determined that it was 8.404 newtons per meter, and I told you that the slope showed up as negative because of the way I had arranged the experiment. And then there was a negative in Hooke's law that means something very specific. But if you arrange the experiment differently, then the k value would not have come up as a negative on here. So knowing that the slope is the spring constant is an important point, and then knowing that there's a negative in the equation, whether or not it showed up as your slope, is another important point for Hooke's law. What wasn't covered in Hooke's law, but we're bringing up now, is that the integral of this graph is this triangle shape, and the integral for this came out to 0.4314 meters times newtons. There's actually a unit for meters times newtons. It's a joule, and in this case, it's a negative because of the way I had to calculate. It's not actually, well, we'll get to when it is a negative and when it's not in one of the following slides here. Let me start out by talking about which forces can do work, and the short answer to that is any force could be doing work, but it's going to show up in different ways. So an external force to your system can do work, and the force applied does what we would call work for the force applied. That's equal to the average force applied times delta x, which is how far the object moves while that force is applied to it, times cosine theta, where theta is the angle between the displacement delta x and the direction of the force. So even though work is a scalar value, not a vector, it's being calculated from these two different vectors, the force and the displacement. Delta x can be delta y or delta z depending on the problem, but you want that theta that measures the angle between the two. If the force is in the exact same direction as the displacement, for example, you're pushing a box to the right and it's going to the right, then that theta is 0 degrees. But if you're pushing a box to the right while the box is moving to the left, then that theta becomes 180 degrees. That work of the force applied is your change in energy of the system. Whether it's positive or negative will not come from whether the force is positive or negative or whether the delta x is positive or negative. Those should actually be absolute values in there because work is a scalar. Where delta energy becomes positive or negative comes from the cosine theta. I think I'll add in absolute values on that on the equation sheet. That should have been here on the slide too. My apologies. Friction can do work, but static friction you're going to have a hard time calculating a delta x if an object is not moving. So static friction isn't going to be the one that's doing work for us. Kinetic friction can do work, and that would be the force of friction times delta x times cosine theta, and that is a change in energy in the system. So for an object that's sliding, the type of problems we've dealt with so far, friction is probably going to be in the exact opposite direction of the velocity of the object. So friction points in one direction and the displacement points in the other direction. So your cosine becomes cosine of 180 degrees. Cosine 180 is -1. So you'll wind up with a idea that friction is usually taking energy out of your system. What it's actually doing is turning that kinetic energy into a thermal energy. And thermal energy, as we mentioned in the previous video, has to do with the average kinetic energy of the particles, which is a level of complexity that we're just not taking it to right now. You can think of it in terms of it turned kinetic energy into thermal energy, and we don't have to pursue it farther than that right now. The force of gravity also does work in various problems, but the work done by gravity is not equal to the change in energy of the system, because the gravitational field that is doing the work should be considered part of your system. This is going to be the case for any force, force of gravity, and then the next one we'll look at is force, the spring force, for which we're talking about a potential energy existing. So as it says here, the work done by gravity is equal to the negative change in potential energy. The reason for that is because potential energy is where you will store the work that the force will do. That's how the term energy I mentioned in the previous video originally came from, the idea or the term for stored work. So if you have energy stored as potential energy, how will that force associated with that potential energy do work on an object? How will that force act on an object? Gravity makes things fall. It makes things fall down. So when things have a lot of height, you're really high, you have a large delta Y, you have a lot of gravitational potential energy. How will that ever be realized? Gravity will pull that object down. And as the object moves down, it lowers its potential energy. Gravity is doing work on the object as the object's gravitational potential energy gets lower. So the work done by gravity or by a spring will always involve lowering the potential energy associated with that force. So work done by gravity equals negative delta U gravity. Work done by spring equals negative delta U spring. Please recognize that's me saying the work done by gravity and the work done by a spring. If you get a question where it's like, what's the work done against gravity by this elevator lifting something up? That's a different question. Or if you're asked, what is the work done on the spring by some person who's stretching the spring? That's a different question. This is the work done by gravity and the work done by a spring. Other forces like tension and the normal force can do work, but unless they are external forces, then they are not work that is changing the energy of the system. So if you just have two blocks that are tied to each other and one is moving the other one, those are internal forces in that type of situation. So they are not changing the energy of the system. They are just sort of transferring it from the one object to the other. I think a lot of this would be more clear with example problems, which is what the next video gets into. In this one, we'll do one to really clarify what that theta is all about. In certain problems, we're going to talk about a surface being frictionless. And in certain problems, we'll talk about a surface having friction. And this image right here is just to show you the idea that at the beginning of the problem over here on the left, you have these different bar graphs of kinetic energy, potential energy, which we refer to in our equation sheet and in OpenStax, I believe, as U subscript G. Actually, is this image from OpenStax? It might be. Regardless, I'm referring to gravitational potential energy as U subscript G. Here they're referring to it as PE. And they're referring to kinetic energy as KE. And then that U that they have with that sort of, what is that, like a green or teal color bar graph, is what they're referring to as thermal energy. And so over the course of the problem, the object, the roller coaster started out with no energy at all on the far left. By the time it's up at part B, then it has all this potential energy. That's because an external force did work on this. You have to have a motor of some sort associated with your roller coaster to lift the roller coaster objects up to the highest point. Then at point B, the motor lets go. This is why it's called a coaster. It doesn't have an engine inside the car. It just coasts. And so as the car goes down the ramp and up the little ramp and down at part D, it's just coasting along and letting its kinetic energy become potential energy, and then its potential energy go back to being kinetic energy. But by the end of the ride, the car has slowed down because some of that energy has dissipated. And what we mean by dissipated is it has gone from being kinetic energy or potential energy into being thermal energy. The reason we use the term dissipated is because you can't then get it back. An object doesn't go fast because it was hot and then cooled off. That energy is just out to the environment then and is only used to heat the environment. It can't be turned back to kinetic energy. In a problem where we talk about something being frictionless, that means that the energy just goes back and forth between kinetic and potential and is 100% conserved. And I'll be really clear, or at least I'll try to be really clear about whether friction is involved. If friction is involved, then energy is not conserved in the problem until you've accounted for work done by friction. Okay, imagine we're given this setup again, and we're asked a slightly different question. How much is the gravitational force between the planet and the block working on the block in this problem? Which would be my wording of it. The textbook would probably say something more like how much work is done by gravity. And there's two ways to approach this. One is to say that work is the force times the displacement times cosine theta. So the work done by gravity would be the force of gravity, mg, times delta x, which is however far the block was displaced in whatever direction it was displaced, in this case 5 meters, times cosine theta. The force of gravity points straight down, and the delta x points this way, so I need to know what theta is. But the problem I'm going to run into now is I just put theta on the screen, and we already have another angle called theta in this problem. So I don't want to get confused. Those are not both 37 degrees. I'm going to change that theta at the top there to phi, just so that I'm not confusing it with the 37 degrees that we already had. So that means that the work done by gravity is equal to the force of gravity, mg, times delta x, times cosine phi now, because that's the angle I want, is what is the angle between the force of gravity and delta x. And that phi is 90 degrees minus 37 degrees because this is a right triangle. So the total work would be mg times delta x times cosine 53 degrees. And that comes out to 1 kilogram times 9.8 newtons per kilogram. I don't want that to be introduced as a negative. We're not talking about the acceleration pointed down right now. Remember, I said I'll put the absolute values in on the equation sheet. The 5 meters is our displacement, and then cosine of 53 degrees was 0.6018. And that comes out to 29.5 joules of energy is how much work is done by the gravitational force in this problem. Another way that you could have done this was that you could have said that the work is equal to the negative change in gravitational potential energy from the top to the bottom. It starts out with a lot of gravitational energy, and by the end it's got presumably zero gravitational energy because we're going to measure the gravitational energy from the bottom. So it started out at 3 meters, wound up at 0 meters, and so I would say that its delta y then is 3 meters down. The work then is 29.5 joules. It comes out to be the exact same, and it should. How much work is done by the normal force on the block in the same problem is something I want to at least mention. The normal force is the only other force acting on the block here, but the normal force is 90 degrees to the displacement, and cosine of 90 degrees is 0. So every time that you have a force that is perpendicular to the displacement, that means that that particular force is not doing any work. It's not adding to or taking away from the energy of the block in this system. It's not, the normal force isn't what's speeding it up or slowing down here, so it's doing no work. That's it for this video. I will put up more example problems